Okay, now we're going to actually talk about what probability is. And to start off, we have to actually define what we call a probability measure. And so we're going to say that if we're starting with some sample space, the probability measure is a function that maps the sample space into the real numbers. Okay, so you think of a probability as really a function. And it's actually a set function. Okay, it's mapping sets into the real number line. Okay, but it can't just be any old type of function. It has to satisfy three conditions, and they're sometimes collectively called the Kolmogorov Axioms, after Kolmogorov, who was a very famous Russian probabilist. And these three conditions are pretty simple. The first says that the probability that a randomly chosen event is in the sample space is always 1. In other words, it's the same as saying the probability that something happens is 1. Okay, that makes sense. The next condition says that for any event, the probability associated with that event cannot be negative. It can be 0, but it can't be negative. Okay? And so these two kind of make sense. We think of the probability as a number from 0 to 1, and we think of the probability of being in the sample space as 1. The next condition is not so obvious, though. It's called countable additivity. And it says that if we have a countable family of pairwise disjoint sets, in other words, the intersection of any two sets is the null set, then the probability of the union of those sets is equal to the sum of the probability over all those sets. That's a very useful fact. We're going to use that a lot. Now, there are certain consequences from this definition. I'm going to point these out. I'm going to leave them as exercises for you to show. The first is that the probability of the null set's 0. The second is that for any finite collection of disjoint subsets of S, the probability of their union is the sum of their probabilities. Notice it looks the same as condition 3, but the difference is that we have a finite collection. Okay? If we have any subset of the sample space, the probability of its complement is equal to 1 minus the probability of being in that set. And for any event, its probability lies between 0 and 1 inclusive. And the last is that if one set's a subset of another, then its probability is less than or equal to the set that it's a subset of. Okay? And these things are things that are all intuitively obvious, but we can prove these right from the definition. So it's very useful. Okay, something that's going to be very useful to us that we're going to use a great deal is we're going to decompose sets. And here's kind of the notion behind it. Suppose we look at A. Okay, we have our Venn diagram, the box is the sample space, and we notice that A partitions the sample space into two sets, A and A complement. So now if I consider any other set B, you notice that B has two parts in a sense, right? There's a part of B that intersects with A, and there's a part of B that intersects with A complement. And I want to show that I can decompose B as the union of two disjoint subsets, where the subsets are the part of B that's in A and the part of B that's in A complement. And I'm going to show how to do this mathematically. So I'm going to use the fact that B is equal to the intersection of B with the sample space. Okay, you can prove that, but that's intuitively obvious. And notice that we just said a second ago that S can be written as the union of two disjoint sets, A and A complement. And so I'm going to substitute that into 1. And now I'm going to use the fact that intersections distribute over unions. And notice that these two subsets are disjoint. Okay, because these elements have to be in A and these have to be in A complement. And so an element can't be in both. Okay. And so notice that I've decomposed U into the union of two sets. This is the part of B that's in A and the part of B that's not in A. And this is a very useful fact. We're going to use this a lot. And how this comes up is in this thing called the inclusion-exclusion formula. And this tells us how to take the probability of unions. So it says that the probability of the union of two sets is equal to the sum of the probability minus the probability of their intersection. Notice why we have to subtract off this intersection, because when I add the probability of A and the probability of B, I'm double counting the events that are in their intersection, and so I have to subtract it off once. Okay? And this is a formula that you can actually prove now. You can also prove two other nice formulas. One is called Boole's inequality. This directly follows from the inclusion-exclusion formula. It says it gives us an inequality based on the probability of the union of two sets. And there's a corresponding inequality for the intersection of the two sets called Bonferroni's inequality. And you can prove this also. Both of these follow directly from the inclusion-exclusion formula. And I'm going to have you prove these as exercises. Now, it's useful to note that there are generalizations. What if we had the union of 3 or 4 or a countable number of sets? Do we have these sorts of, formulas? And the answer is yes. This is the generalization of the inclusion-exclusion formula to a finite number of sets. And notice how it works. We take the sum of the probabilities subtracted from the sum of the probabilities of the pairwise intersections, add that to the sum of the probabilities over all the intersections of any 3 distinct sets, and we keep doing this. And notice what happens is we keep changing the sign, and we look over the intersections where we increase the number of sets being intersected by 1 until we get to this final term. Again, you can prove this, but I'm not going to ask you to. It's tedious. And Boole's inequality also generalizes, as does Bonferroni's. Okay. And again, I'm not going to ask you to prove this, okay? But it's useful to know. One of the things we're interested in a lot is conditional probabilities. So we're going to have two events A and B where the probability that B occurs is not 0. And what we're going to want to know is this. Given that I know event A has occurred, what is the probability that knowing that the event B occurs, what is the probability that A occurs? Okay. Here's kind of a Venn diagram to help us out with this. So we're going to say, okay, we're going to suppose that we're in B, and now we want to know the probability that A occurs. Okay. And it's given by the following formula. This left-hand side is read as the probability of A given B. And here's how we compute it. Okay, this is the definition. Now let me show you why this definition makes sense, okay? Notice that what we're saying is given that B occurs, so we already are in B, okay? And we want to know the probability that A occurs. So we want to know the proportion of the elements of B that are also in A. So this definition comports with what we think it should be, okay? Notice that B kind of takes the role of a sample space now. This becomes our new universe because we're told that we know B occurs. So now we know for a fact we're in B, and B takes the part, plays the part of an actual sample space now. Okay. Where does this come into play? It's very important in understanding independence. There are a lot of different definitions of independence. I'm going to show you one. We're going to come across another one later on. We're going to say that A and B are independent if and only if the probability of A given B occurs is the same as the probability of A. Or this is actually equivalent to showing that the probability that B occurs, given that we know A occurs, is equal to the probability of B. Now before we get into this, it's really useful to think about what independence means. It's one of the most misunderstood concepts in statistics and probability. And I'm going to ask you to prove as an exercise that 1 is true if and only if 2 is true. But I want to give you some intuition as to what this means. Let's think about what the probability of A given B complement is if we know that this condition is true. Okay, if I know that probability of A given B is equal to the probability of A, then what is the probability of A given B complement? I want to work this out from first principles. Okay, so by definition, this is the probability of A intersection B complement of the probability of B complement. And notice that this numerator is basically the portion of B that's in B complement. And we showed before that the probability of A can be written as the sum of the probability of A given B plus the probability of A given B complement. So I can rewrite the numerator like this. I know that the probability of a complement is 1 minus the probability of the event. Okay. And I'm going to use the fact that this condition here tells me that the probability of A intersection B is the probability of B times the probability of A. You can verify that. When I factor out the probability of A, I get the probability of A left. Now notice what this means. This means that the probability that A occurs is unaffected by whether or not we know B occurs. Okay? So knowing whether or not B occurs gives us no information on A. And this is what independence means. It means that knowing that B occurs gives us no information on A. That's what independent means. It means A occurs the same either way. Okay? It's very important to understand that if this condition occurs, this does not imply independence. Okay, because it's equivalent to saying that the probability of A intersection B is 0. If you go back to this definition, in order for the conditional probability to be 0, it's telling us that the intersection of A and B is disjoint. Okay? And notice that disjoint is the opposite of independence. It's the exact opposite. Because if two events are disjoint and I tell you that one occurs, you know for a fact the other one cannot occur. So it's important to understand from an information point of view that disjoint is the opposite of independence. And people often think that they're the same. They aren't. Okay, that finishes up for the basics of probability that we need to know. We're going to get into the nuts and bolts and the details of see how we actually use this in the next couple of videos.